Okay, so welcome back to the discussion session. Maybe more people are still coming. I see 50, but okay, let's briefly get started. And in fact, I would like to share my screen now. And don't be afraid, I'm not going to give an additional talk. I just want to show you a brief collection of questions which came up, and basically there had been 2 or 3 sources. One of them is simply that the speakers had been asked before to send in questions to be discussed in the discussion session, and some of them did, and I just want to list them here briefly, not going into detail yet, just to see what came up. And so these are the main questions by Tomas Brauner, and I don't want to read them explicitly, but basically he was asking about experimental signatures, which is something we have not really discussed so far. And also in the chat, the question about astrophysical consequences came up, and maybe this is also related to this. So yeah, so are there any experimental signatures, since theory is difficult, which could tell us something whether or not inhomogeneous phases exist? And the other question is about QCD. So we heard a lot about models, but of course, Tomas himself also talked about QCD. So are there any long-term prospects for detecting inhomogeneous phases on the lattice in QCD or in QCD-like theories, which he discussed by himself? Mark Wagner had partially the same question. So do we expect that inhomogeneous phases exist in QCD? And also he was asking for other QCD-like or inspired models without sign problems where one could do this on the lattice. Okay, there was a long list by Martin Steil with questions, which I don't want to read here. So they are mostly very detailed questions also to the FRG treatment of inhomogeneous phases. I suggest, so these questions are around, and anyway, it's not that I have now to read these questions, but of course, all of you and all the speakers could raise questions now during the following discussion, which they think they should be discussed. And I also wrote down my personal questions, and actually I did so before looking in detail into the questions which had been sent to me, and I noticed that they have quite some overlap with the others. Also, I was asking about the situation in QCD, and actually these 2 figures had already been shown earlier by Stefano. So there had been some QCD approaches or calculations starting from the QCD Lagrangian. One of them was in Dyson-Schwinger with some simple truncation, one has to say, but there an inhomogeneous phase indeed was seen, and the other one was the FRG calculation by Wei Fu, Jan Pawlowski, and Fabian Rennecke, and they also found some region where there were some indications of possibility of an inhomogeneous phase, even though this is not completely conclusive. So maybe one could discuss this further, and maybe Jan will even talk about this in the next talk after the break in the next session. Okay, and my other questions related to this are also very similar to what was already asked by Tomas and Mark. So is there a chance to study inhomogeneous phases on the lattice within QCD even, either by some novel approaches which could be applied to finite mu, or by a clever choice of parameters? So this was something which Stefano briefly discussed in his talk. So is there maybe a way that we can manipulate the parameters, masses, or other things in QCD such that inhomogeneous phases even appear at low mu or mu equal to 0, where there's a chance to study them on the lattice? Now, my other question is something which was actually also addressed in Andreas Wipp's talk, namely, what is the role of baryons? So we have seen these kinds of density, so what is shown here is basically the density distribution in these real king crystals or soliton crystals. And so these are the solutions which typically come up in 1D, either in really 1+1 dimensional models in the Gros-Neveu model, but also in the 3+1 dimensional NGL model if you restrict the modulation to one-dimensional ones. And what you see here is something like if you go to very high density, you basically are in the restored phase and the density is simply homogeneous. But if you then let the matter go, it will expand and eventually these peaks will come up. And you can identify them somehow with single baryons. So in a way, this is some kind of hadronization. And so the question is this indeed some way which also occurs in QCD? And could this lead to some kind of crossover deconfinement transition at low T, which is also pushed forward by some people in the context of neutron stars, for instance. Okay, so these are the points raised by the speakers and by myself. But anyway, I mean, there are, of course, your questions. And I think rather than me asking questions or the speakers asking questions, of course, you should ask still questions to the speakers. We didn't have so much time directly after the talk. So, I mean, there are questions directly related to the talks, but also questions which had not been raised. And to the first part, there had been several questions already in the chat. And also this was given, no, this is wrong. So there are, this is just, I don't read it, some questions which have been in the chat. The chat, of course, always has the problem that these questions come up during the talk, and the person who definitely does not read them, I guess, is the speaker. So I really would encourage you to ask these questions now openly in this discussion and maybe directly ask them to the speaker. And so I just stop sharing my screen now and maybe just ask whether there are maybe direct questions to the talk still, which should be clarified. Maybe those which have been already in the chat. Is there anything you want to ask? Okay, I mean, yeah, Julian Lenz had the problems with his mic, so maybe it works now. Please try.
Hello? Hello?
Yeah,
Okay. Yeah, I actually had a couple of questions about the talks. I remember that I wanted to ask Mark Wagner, if you now have these inhomogeneous solutions that are still one-dimensional modulations, could you start from there on a stability analysis and look if you have like at least the possibility for two-dimensional modulations there?
So Mark, do you want to answer?
I think it is possible, but maybe I can forward this question to Mark Winzel, who is also in the audience and who is a real expert in the technical aspects of this work.
I mean, I think in principle this should be possible, of course, but you have to remember that, for example, these local inhomogeneous modulations that we found within the homogeneous broken phase, so these local minima, they already weren't connected by a second or by an instability. So there's always this possibility of first order transitions, of course. And even if you look at finite lattice spacing, for example, and compare these minima, I don't know whether you will find a two-dimensional answer via stability analysis. So of course this can be done, but of course a full minimization would be perfect.
Also, my guess, at least from a physics point of view, if there's something new coming in by two-dimensional modulations, it's probably not a simple thing. It's more maybe a localized excitation in both dimensions. And this is quite different than from the 1D modulation where you want to start. So I think it's possible, but even if we would be able to do it, we would still be not sure, have maybe doubts whether we got an interesting thing which could appear when you allow two-dimensional modulations.
So
Okay.
if I comment to this, okay, I'm the discussion leader, so I may, I guess. So within the stability analysis, which in a way, I mean, this is the one which was introduced by Stefano and Lennart in the continuum, but which you also use on the lattice, and I think the idea is basically the same. You wouldn't even be able at the phase boundary to distinguish between one and two-dimensional modulations, because you find one wave number which becomes unstable at the phase boundary, and all the modulations which you can build with this particular wave number Q, and this could be one-dimensional, two-dimensional, simple plane wave, so this chiral density wave or a sine, they all become unstable at the same point. So this is also what is seen if you perform model calculations with a particular ansatz. So on this phase boundary, they all become unstable. I mean, these phase boundaries all agree. And if you go inside the phase, the inhomogeneous phase, then of course, some of them are more favored than the others. So for the stability analysis, I wouldn't even see a difference. Of course, the true minimization, this might be different.
Okay, but still, I mean, I see the point that in a finite volume, we usually have to fix our modulations into the box size. So there will probably not be like one direction where this can be minimized, because it will first have a little bump. But nevertheless, if you could do this in infinite volume and you already are in an inhomogeneous solution, there would be the possibility maybe to get to another inhomogeneous solution, or what am I missing?
So I would say this is correct, yes. I don't know. There are other.
In principle, this should be possible, yes. So this should be possible, yeah. Not only in principle.
So maybe I can also add one point to this. There was another figure shown by Stefano at the beginning where he compared different modulations in the NGL model, and he also included two-dimensional ones, which turned out to be not favored over the one-dimensional ones. But what he did not show is that he also performed this calculation at higher values of mu in a regime where we don't quite trust the model anymore. And for the experts, you are inside this inhomogeneous continent and things like that. But there things turn around. So it seems that at higher mu, inhomogeneous two-dimensional modulations became more favored than one-dimensional ones. And that actually was in line with some predictions also made in the context of quarkionic phases, where there was also the prediction that if you go to higher and higher chemical potentials or densities, then more and more modes just superimposed, and you may get more complicated structures. And that would be interesting maybe to understand a little bit better, because well, okay, the models, you always have the problem that you run into a regime where you don't trust the model anymore.
Yeah, but if I remember correctly, even in what you call the island, the inhomogeneous island, I think in the solid state physics community, they really have results where they go through several phases of first one-dimensional modulations, then two-dimensional modulations, all in this small region, what you call the island. So yeah, it seems kind of unnatural that we have these one-dimensional modulations. Yeah.
So in a way, this is actually just the opposite of what I would like to see when I showed this schematic picture in the end of my slides, where I said if we go to very small densities, it would be nice to get single nucleons somehow. So, and they should be three-dimensional, of course, in the 3+1 dimensional world. So I don't know how this fits together.
Yeah, I see. Hmm.
Okay. I see a question by Gerge again.
Yes, this is actually a follow-up to what I asked Mark.
Yeah, right.
But actually, it's related to this discussion now, so I thought I bring it up again. So, Mark, I understood in the meantime that I misunderstood, but so my question was not that correct in the sense that you are not doing this sigma path integral. You're just looking at the action as a function of sigma, and you are numerically minimizing it, right?
Yes.
Okay, good. But then couldn't you just do the path integral over sigma and allow arbitrary inhomogeneous configurations of sigma and look for what are the relevant configurations? And then you might find one-dimensional or two-dimensional or whatever is preferred kind of modulations.
Yes, this is in principle what Andreas Wipf discussed in his talk. In 1+1 dimensions, we are doing the full simulation.
Yeah, I know, but in 2D.
In 2D, but of course, at some point, it gets very time consuming. I mean, you yourself, you need to do several mu and t, and when the dimension increases, the cost explodes. So
yeah, but I mean, it's a scalar field theory, so I think
there is a determinant. It's a fermionic, not a scalar one.
Mm-hmm.
Do you hear me?
Yes.
Yeah. So Gergely, we did first simulation in 2+1 dimensions, and but you shouldn't forget. I mean, it's at chemical potential. You have to make a phase diagram. So it is some work.
Yeah. No. But I mean, in principle, it's doable, right?
It's doable, of course. Yes.
Yeah, it's just a matter of computational.
But it took us some time to take the correct fermions, right? For example, we know with staggered fermions, they are problematic in some of these models that we know. Anyway, we have done it with chiral fermions, and as I said at the end of my talk, at the moment we have no indications of inhomogeneous condensate. And we don't assume anything about the particular form of the condensate. It should come out of the simulation, as I say. So we have to do more simulations, but we did some scan, a first scan, and unfortunately we did a momentum decomposition, and we didn't see any peaks in the momentum space. Which squares with what we have seen from the variational method explained by the Frankfurt group.
So may I ask, was this done also for a finite number of fermion filters?
Sure.
Oh, okay. Because I mean, then of course this is double hard, because naively you would expect that at infinite number of fermions, so in mean field, this is the best situation to find.
Right. You're absolutely right. If you don't find anything in NF go to infinity, you go to NF equals 2 or 4, as we did, the fluctuation increase, and you're right, of course. Yeah. But you know, you may nevertheless miss some directions.
That's right.
Minimization, so it's not completely clear. May I say something about what Tomas Brauner asked, or do you want?
yeah, I also wanted to go eventually to this direction. I see. Okay, yeah. Maybe we will come back to that. I saw another question by David Blaschke, so maybe.
Yeah, hello, maybe I can ask a question which I always have in this context, and which is also a bit related to the direction of astrophysics. When we go to the very low temperature region of the phase diagram, there is this color superconductivity region, and from phonological models like NGL, we know that chiral symmetry breaking and color superconductivity kind of expel each other. And so one would expect, if we discuss inhomogeneous phases, that the regions where chiral symmetry is restored are then filled by some color superconducting condensate and vice versa. Has anybody meanwhile done models like this? I mean, Michael, you are doing NGL models and you have these big physics reports. So in principle, you should have everything in your hand, but
yeah.
This was, let me just put this question first in the room. And the second is shortly, I wanted to say, okay, this, what has been discussed by Hatsuda and Baim and so as the crossover in this region, in the phase diagram, also for compact stars, is basically the coexistence of these two order parameters, and that they change in a continuous way when they form, so to say, a coexistence region. And in this sense, both questions might be intertwined. Okay.
Mm-hmm. So by coexistence, you mean just the chiral and the dicquark?
Exactly. Yeah, because they have this triangle diagram evaluated where the mesonic condensates and the dicquark condensates with strangeness then are coupled to each other.
Yeah, in fact, I mean, there has been old calculations already in 2003 by Zatsikovsky, who found a solution in an NGL model of a coexistence of a chiral density wave and to a C, homogeneous to a C phase. And recently, a student of Dirk Rischke, Philippe Lacachus, has also looked into this again. And so this solution could actually be generalized into a way that also these more favored inhomogeneous phases like the soliton-like could be treated together. And so then one finds indeed, I mean, in NGL, everything depends on parameters and on the other circumstances. So one finds indeed a region where these two could coincide at low temperatures. Now, if you increase the dicquark coupling, then eventually the inhomogeneous phase will be kind of pushed away, and the color superconductor wins. But all these calculations, again, I mean, you are interested in compact stars, of course. All these calculations have been performed at zero isospin chemical potential. And this is a situation where these homogeneous to a C phase, of course, is very strongly favored. But as you know, as soon as the up and the down quarks get different chemical potentials, this is a strong penalty for these phases. And so now what one would have to do is to study this under compact star conditions with neutrality and beta equilibrium. And this has not yet been done. So.
Okay. Mm-hmm. Thank you.
Okay, yeah, maybe then indeed, since Andreas Wipf wanted to ask a question to Tomas Brauner, maybe you can do this now.
I believe he wanted to answer my questions.
He wanted to answer you. Sorry, this I misunderstood completely.
I hope.
Okay, maybe then let's do that.
Muted.
Andreas is muted.
Okay. So can you unmute yourself?
Is it now okay?
Yes.
Yeah. You hear me?
Yes, we can.
Yeah, okay. So it was, I think, the first question which Michael showed us, the first slide. Well, whether we have any chance in QCD or QCD-like theories to say something about this inhomogeneous phases. Well, about real QCD, there's not much to say. I mean, it depends on the progress we are making, of course. I can say a bit more about QCD-like theories. These are two color QCD, and the one which you mentioned was G2 gauge theory, which, as you know, we investigated some years ago. And we went to very high, reasonable high chemical potential and calculated this condensate and how the condensates really, the thresholds and so on. It could very well be that the mu is big enough to see an inhomogeneous chiral condensate in this calculation. But it would be really an effort. So, it's not QCD, it's QCD-like theory. And I'm a bit skeptical that anybody will, this would be a project for 2 or 3 years, I assure you. To get this result, which we got, lots of computer power and several years of work. So maybe SU2 is a bit more friendly because it's easier to simulate, and of course, who cares about the number of flavors in this calculation? Well, but we would have to ask, Lawrence, for example, Smekar and these people, and Simon Hans, who did calculation for SU2. It may be within reach, but it's an effort. That's what I want to say.
Maybe if I can very quickly reply to that. So what I showed at the very end, so our prediction is that this specific phase, the chiral-soliton lattice phase, is the more likely to show up in the phase diagram the larger the gauge group.
Yeah.
Unfortunately, that's bad news, of course, because
G2D is 7, right?
Yes. Yes.
It's quite small, the number 1/2D.
Yeah, maybe then I ask directly my question to Tomas. So since you had some kind of handle to QCD by using this effective theory, even though then you needed this strong magnetic field. And at some point of your talk, you said that it's of course not it's of course not a coincidence that you all find all the same things like these Jacobi elliptic functions and things which had been found in the models without magnetic field. So the question is there anything? So first of all, how can we understand this? And second, is there anything one could learn from these kind of effective theories for the case without magnetic field?
That's a very interesting point, and unfortunately, I'm not an expert on for instance, on the Gross-Neveu model or the Turing model to really answer in detail. But so the solution that we found are basically soliton solutions of the Sine-Gordon theory in 1+1 dimensions. That the physics becomes 1+1 dimensional because of the magnetic field. So in that sense, it boils down to the same number of dimensions. Now, probably others, maybe Andreas Wipp, could say exactly what the relation between the Gross-Neveu and or Sine-Gordon model is. If there is a duality between Sine-Gordon and Turing model, right? So I'm not sure if the solutions are mathematically identical, but it shows up that qualitatively they are very similar. And so if I may actually make a comment on what Andreas Wipp showed in his talk. So it's interesting that, for instance, the phase transition between the uniform phase with the uniform chiral condensate and the phase with this solitonic and non-uniform phase, it has a very similar nature. So it happens via the formation of a domain wall, where subsequently the domain wall starts to sort of get squeezed, and you get like a lattice of domain walls later on in higher magnetic fields and higher chemical potentials. So one thing that actually we are currently trying to understand is that if there is some kind of universal description of the phase transition itself, if you think of ordinary uniform Bose-Einstein condensation, say in QCD with isospin chemical potential or two-color QCD with baryon chemical potential, right at the condensation point, at the phase transition, you can describe the condensate as a non-interacting Bose gas. It's something that has been shown by Kim Splithoff and collaborators who worked on this. it would be very interesting to see if there is a similar, model independent, if there's some universal behavior here, where, because the physics becomes effectively, again, lower dimensional. The transition between the uniform and non-uniform phase is via formation of a domain wall. So there, whatever fluctuations you have, they are localized on the domain wall, for instance. So there may be some way to understand at least the transition, describe it without having to have a concrete model.
Mhm.
But maybe Andreas Wipf knows.
Actually,
can comment on that.
I see Rob Pisaski raised his hand, so maybe he can also comment to that. Or
Thanks. I'd like to make a comment that I don't believe has been raised at the outset. Let me say that what I'm talking about only applies if you have Goldstone bosons, so it doesn't apply to the Gros-Neveu model where you break Z2 or the chiral Gros-Neveu model where you break U1. But if you have a ON model where n is bigger than 2, then you can, in the linear sigma model, sit down and just very straightforwardly compute in perturbation theory, and you find that for a chiral spiral, the Goldstone modes have a double pole at non-zero momentum, which gives rise to, this is work that I did with Alexei Spalek and Semyon Baldassar. Logarithmic infrared divergences at 0 temperature and power-like at non-zero temperature. And based on a large N analysis, we found that you actually go, instead of to a chiral spiral phase, to a peculiar symmetric phase, which is analogous to a quantum spin liquid. And I looked through the talks. Unfortunately, I didn't get up early enough to listen to all of them, but last night I looked at them. And my question is really to Martin Steil and Buballa, that they should compare to you and Martin to a symmetric ansatz. That, because you looked at theories where you would have Goldstone bosons, right? If you had a uniform condensate.
right, yeah.
And so I just wanted to ask if you had done that and to point out the relevance.
So can you say again what you mean by symmetric ansatz? So,
you don't spontaneously, it's, you have a peculiar propagator, but it's isospin symmetric, and you don't spontaneously break rotational symmetry. It's actually numerically the simplest thing to look at, right? I mean, but you're going to have a dispersion relation where, because Z is negative, Z is the coefficient of the term quadratic in differential derivatives. It goes down and then goes back up, but there's a gap. It doesn't go all the way to 0. If you get a condensate,
yes,
it goes
right.
to 0.
Yeah, I think I don't know whether Martin wants to comment on this. Of course, this negative Z was also even seen in this QCD paper by J. Fu and Pawlowski and Fabian Rennecke. The question is indeed whether it goes, how deep it goes. So Martin Steil was discussing now a particular explicit calculation with the chiral density wave ansatz. But he and also we are in contact to others who perform, of course, these kind of stability analysis. I don't know, Martin, you want to say something?
Yes, so maybe to elaborate a bit, in this talk, I mainly had to focus on this RG-based mean field computations and getting those to a point where we can trust them and where they are in agreement with existing results. And now that we have understood how to perform these kinds of calculations, the natural next step, of course, would be to compare to those results from the stability analysis. Because actually those results with the chiral density wave have to be in agreement with the results from the stability analysis. If they aren't, there would be some further inconsistencies. So this is definitely something which we are looking to do and which is reasonably simple to do because, as already mentioned, those computations with the stability analysis are based on an homogeneous ground state. And we already started computing observables related to two-point functions. So it's definitely on the agenda and on the horizon. But for this talk and at this point, I did not bring results regarding those comparisons.
Yes, I noticed that on your last slide, and I just wanted to encourage that, relative to all the work you've done, it's a very simple thing, and I think it'd be very interesting. I also just wanted to say that I found the work by Jan and Wu and Fabian Rennecke very interesting. And I wanted to emphasize another point which people had brought up, and that is the physical relevance, that what they also found is that the width of the critical region is very small, whereas the width of the region in which Z is negative is much larger.
Yes, yes.
And that's something that people who work on critical endpoints, I heard a talk by Shreyas yesterday, really seems to have been neglected, because, as I'm sure you know, you have to get the sigma mass way down to see any critical fluctuations, and that's hard. Getting Z negative is not hard. Thanks.
Yeah, welcome. So I don't know, I see raised hands again by David. Is this a new raised hand or a new question, or?
No, sorry, I should lower the hand.
Okay, okay. Okay.
If there's no follow-up to this topic, I would like to ask a different thing.
Sure.
Yeah, I would, in a certain sense, come back to my talk and the talk of Leonard Kurt. I mean, what we presented is that there's a dependence of inhomogeneous phases, at least in the 2+1 dimensional Gauss-Neveu model, on the cutoff, and it seems that the cutoff favors the existence of inhomogeneous phases. So my question to the audience and to your, what are your opinions, for example, whether we can or should trust models like the NGL model in 3+1, which has a cutoff, which is supposed to model QCD. I mean, is it really worthwhile to study these models and to make conclusions to QCD, or not? And also maybe related to Andreas' talk, what kind of model should we try to simulate in the future on the lattice? I mean, we cannot explore many different models at the same time. It's just too expensive. We would like to make a wise decision, and here suggestions are very welcome, or opinions.
Maybe if I may, I can't raise my hand because I'm co-host, but
yeah, sure.
I may start. So, I mean, in the quark meson model, you have in principle the choice to remove the cutoff by taking the renormalized limit. But what you can also do are these RG consistent mean field studies where you fixate your initial action at an intermediate scale, which I call lambda prime. And then there you can really study the effects of vacuum fluctuations while still maintaining RG consistency. And this is actually a rather interesting point, because for practical reasons or in full FRG computations, it might not necessarily be sensible, for example, for the quark meson model as a low energy effective theory of QCD, to specify your action at an extremely large scale, because you know that your model isn't valid there anymore. So I think that models which have a cutoff, or in the case of the quark meson model, where you don't necessarily have to remove this cutoff, it's interesting to study those effects and also to perform computations at a finite cutoff if you so want. But at least for the quark meson model, you should always ensure RG consistency, because if you don't, then you basically violate an underlying principle of the FRG, and that is that the initial condition has to include all fluctuations. But I mean, in this RG consistent framework, which Jens Braun and Mark Leonard and Jan Pawlowski discussed and introduced, this can be studied quite nicely with the FRG. And I did not do this to the fullest extent yet.
Yeah, maybe I can just add to this, just phrase a few things in different words. So, I mean, what was behind Mark's question was basically, okay, we have the 1+1 dimensional Gauss-Neveu model, and there it seems infinite number of flavors, but even at finite number of flavors, so including fluctuations, there is an inhomogeneous phase. At the 2+1 dimensional Gauss-Neveu model, we saw that as soon as the cutoff goes to infinity, the inhomogeneous phase goes away. And then I guess this is behind Mark's question, if you now go to 3+1 dimensional model, so which should be closer to our world, but there you cannot remove the cutoff in these 4 fermion models. And so then there is, of course, the possibility that the whole thing is just an artifact of the cutoff. And what Martin just pointed out in the quark-meson model in 3+1 dimensions, you can send the cutoff to infinity, and as Stefano has shown in the morning, you still get an inhomogeneous phase in mean field calculation at least. So this is what we know so far. Although if you look more closely, then there are some problems with this treatment. So at least in these mean field calculations, it's also well known that eventually for large cutoffs, the spectrum is not bounded from below, and so the potential is not bounded from below. So we run into some severe problems there. So the question is maybe back to Martin. If you now treat this within the RG scheme, would you then have these problems still, or?
When one talks in this RG consistent mean field setting, then you basically encounter the same problems, because if you take the renormalized limit in mean field, the result should not depend on your regularization and renormalization scheme. So the results in principle from Pauli-Villar regularization, dimensional regularization, and FRG should coincide. And at least for dimensional regularization and Pauli-Villar regularization, I know that they do. So, I mean, in that sense, the FRG is no cure there. But if you talk about the full FRG treatment, so including bosonic fluctuations, then such a scenario is basically excluded by the flow equation. But in order to answer this question, one would really have to go beyond mean field, which we are planning with our proposal.
Interesting.
Maybe if I can make a comment / question to Martin style, and I think that opens a new topic, and that's I was wondering how much effort it's going to take to include the effects of the bosonic fluctuations in the RG, because as we know, the physics in different dimensions is very different, and in 3+1 dimensions, such one-dimensionally modulated order parameters that are favored at mean field should be unstable at any non-zero temperature, right? They should not. There's this thing called Landau-Peierls instability. It says that there should not be any long-range order, at most a quasi-long-range order, so a polynomial decay of power law decay of correlations, and it's absolutely critical to include the bosonic fluctuations to see this effect.
Mm-hmm. Can you hear me? I'm muted.
Yeah.
Okay. So yes, I mean, for the chiral density wave, we basically have the flow equation, which includes the bosonic fluctuations. We just have not discussed the numerical solutions. There are two reasons for this. The first point is we wanted to have a starting point which we understand, which is why we tried to reproduce mean field results, which turned out to be rather complicated, as I discussed. But we are currently at the point where we understand our mean field results and where we can really start to attempt a full numerical solution, including the bosonic fluctuations. I mean, this is a bit technical, and it's a bit I don't know if you want to go into detail, but the problem there is that you, if you include the bosonic fluctuations, really have to solve a partial differential equation, which includes two-dimensional momentum integrals when you consider the eigenvalues of the chiral density wave. And I mean, you have to use a good numerical scheme for discretization of this partial differential equation, and then a good time stepper for integrating it. But in our CRC and in our sub-project, we have developed such methods. And in the next months, we plan to apply those methods to the LPA flow equation with chiral density wave condensates.
Are these spectral methods? Or?
No, explicitly not spectral methods. I mean, if you, or it depends on what you mean on spectral methods. I mean, these flow equations are basically advection diffusion equations. So you need to use shock capturing schemes, and we are currently using finite volume methods for spatial discretization in field direction, and we use a semi-implicit finite volume scheme. So we still have the scale, the RG scale direction. We don't discretize. So basically end up with a finite volume system, a method of line system. But the important part is that you need a shock capturing scheme, because these RG flow equations are really flow equations in the true sense of the word. Their stuff is flowing and shocks can develop due to different reasons. And so you can't really use global method or Taylor expansion or naive finite differences.
I mean,
so what do you expect to see actually? If when you integrate out all the fluctuations, the long range order should die away. How would this show up in the
I mean, the
integrated flow
expectation would maybe be that the inhomogeneous window, which we find in mean field, then disappears if we include the fluctuations. If it does not disappear, then this could be related to various things. For example, that our truncation is not sufficient because we just consider this local potential approximation and we don't consider stuff like wave function renormalizations and so on. So in terms of the flow equations, the propagators there are rather simple and might not be sufficient to capture all physics there. But I mean, all of this is very hard work, both numerically and conceptually. So we have to see what happens.
I think I like your work very much, because it's one of the first cases where we have the flow equation understood for non-homogeneous backgrounds. But can you go away from the plane wave? I mean, it might be very hard, but...
Yes, I mean, this was one question which was in this A4 text block, which Michael flashed briefly. I mean, this whole idea of treating inhomogeneous condensates in the FRG is based on an analytic diagonalization of the two-point functions. And it's basically, I think, hopeless for, let's say, some Fourier ansatz. If you maybe look very, very closely in literature, you might be able to construct or find unitary transformation for the King crystal. Because I mean, I don't know, if you re-engineer something from the eigenvectors there, then you might get lucky, but I think this would be extremely complicated. I mean, this approach currently is very limited to the chiral density wave, and because of this also to the chiral limit. I think if you want to go away from this, the most reasonable thing to do would be to stick to stability analysis, because I don't see how you could do numerical diagonalization during RG scale evolution. I mean, even in mean field computations, this is extremely expensive, as Stefano knows. And if you have to do this at all RG time steps, I think it will be numerically almost impossible.
I think the bad thing is indeed, as Tomas said, that we would expect that one-dimensional modulations should not survive the fluctuations at finite temperature. And so exactly, the one which you can treat, the chiral density wave, should not survive. And even if you managed with hard effort to find something like a real King crystal, it's still one-dimensional. So I think indeed the stability analysis would be very important in order to see whether there are hints about other possible fluctuations, but modulations.
Maybe one point to this.
Yes.
I mean, one thing which one could also try is basically to extract Ginzburg-Landau coefficients from the FRG computation, and then make a Ginzburg-Landau analysis around the critical point with this non-mean field Ginzburg-Landau coefficients. And there you could treat arbitrary spatial modulations, but then you could only get a solution very close to the critical point. But this could also be one way on how one might be able to explore higher dimensional modulations. But then you are facing this high dimensional minimization problem, which in itself is difficult, as our lattice colleagues know. If you try to minimize, I don't know, 50 parameters or so, it's a very hard problem to be sure that you find a global minimum.
Yeah, talking about fluctuations, maybe I would like to come back to these 1+1 dimensional simulations with finite number of flavors, which seems to contradict these Mermin-Wagner theorems and things like that. So how sure are you that this is not a lattice artifact?
Yeah. So of course, I think we did a careful analysis, finite size analysis, and going to the continuum limit. I think I showed you some of the results. So they're sort of robust. We did our best what we can do. But at the end of the day, we cannot really answer the question whether it's in the strict sense a spontaneous symmetry breaking or whether it's long range order. It's if you have, it may be that the correlation functions, for the order parameter decays like 1 over x to the power 1 divided by 8 for 8 flavors. There's a conjecture a calculation even for a simpler model by Witten. And we looked at that and tried to take all kinds of fits by taking different assumptions about the type of the phase. It looks most probable like it is within a spontaneous symmetry breaking, but we cannot be for sure. Right? If you look in our paper, I mean, we did a careful analysis. Now, actually, Tomas is here, and he did very nice work on the role of the Goldstone bosons in case we have not the usual dispersion relations we are used to in relativistic field theory. To put it short, I mean, the Goldstone theorem, which I thought is sort of, some years ago was very clear to me, it's not that clear anymore. I mean, you really have to distinguish at finite density different types of dispersion relations. One, the relativistic one, the non-relativistic one. And depending on the dispersion relations, the counting of Goldstone bosons is different. Okay. I mean, you can have a boson, a non-relativistic boson in 1+1 dimension. Right? A relativistic boson massless does not exist in 1+1. In addition, you have to distinguish whether the symmetry you break is an inner symmetry or it's a space-time symmetry. Again, the counting may be different. In one case, you get an inequality, and the other an equality of the number of Goldstone modes. Okay, so we looked a bit into that, and so there's a distinction of Goldstone bosons according to this dispersion relation, or there's another which is actually due to Tomas and collaborators, an algebraic distinction between Goldstone modes. It could be that the Goldstone model completely decoupled from the system. It could be that it is a non-relativistic Goldstone boson, which wouldn't be problematic. Or it could be, in the strict sense, there's no spontaneous symmetry breaking. It's a causaless-Soulless type phase. Yeah? If you would ask me what I think is most probable, I think I would say it's a non-relativistic scalar particle and spontaneous symmetry breaking. But again, we cannot, of course, prove it on the lattice. It's hard to prove anything, but it's most plausible at the moment.
Yeah, actually,
and of course, in a very for a big baryon density, we don't expect a relativistic dispersion relation anyhow. I mean, there are models where you can work it out. It's not relativistic. So this would square to what I'm saying.
Yeah, I found also your first part of the answer I liked very much, and I think I find it very physical even to say we don't really know whether it's just very long range. I mean, this is also in the context of this Landau piles instability. There was an old paper by Bengt Vriemann and Gordon Bain in the 80s about pion condensation in neutron stars, and there was the same thing. I mean, if you look at the expected periodicity, which could be several kilometers, which is larger than the size of the neutron star, then it doesn't really matter. Then it would still look, it's like liquid crystals. It looks like periodic, and this is fine. So in that sense, I even find it sometimes misleading if you have these no-go theorems and
yeah.
Nice.
There are materials in atomic physics, which show this long-range behavior where it's polynomial decay of the correlation function. So this system exists, and there are many of those in nature. Actually. May I add a question here, which I sort of, are we running out?
No, it's fine.
This is maybe my ignorance, but it seems to me that somehow that's related to the piles instability. It seems to me that the existence of inhomogeneous phases is somehow related to the existence of a first-order transition if you restrict to the homogeneous case. Okay, so I mean, you have metastable state if you have first-order phase transition, and the system can oscillate between different metastable states and produce inhomogeneous condensates. This goes together with the observation of Mark Wagner and his collaborators that if you remove the cutoff in 3 dimensions, the first order transition goes away and the condensate goes away, inhomogeneous condensate goes away. There are these type of observations. So I'm just asking for those who did lots of model studies, is this just a wrong statement or?
It's not entirely true. So there is this was also partially discussed by Stefano in the beginning. There are very many models where you can even analytically show that the tricritical point and the Lifshitz point coincide. But there are counterexamples. So for instance, he showed when he includes an additional vector interaction, this goes away. When you introduce a third quark flavor with some Toft type coupling, it goes away. So it seems to be related to particular interactions. And also in Mark Wagner's and Leonard's talk, one could show that the two, at least in the continuum, they agree. So when one goes away, the other one also goes away. But there are counterexamples.
Yeah, this brings me maybe to Stefano's talk. I mean, he said he included a vector coupling and said it's essentially the same like a chemical potential. Some months ago, I did also some calculation in this direction. It's of course not completely true. There's an imaginary I in between, which may make a difference. And I'm sure about this I. So maybe I missed something there, but okay. We're also involved in this calculation, right?
That's right. I mean, maybe Stefano wants to answer, but since I'm already talking, so whether or not there is an I depends on whether you are working in Minkowski or in a Euclidean space. So
okay.
There's not always an I.
No, but I can easily switch in the large n limit from one to the other by multiplying with gamma 0 or something like that. Okay. Anyway, you are sure about it, I guess.
Okay, so we basically reached the hour. We have not yet discussed all the questions which came up, in particular about possible observables. But I don't know.
Yeah, we can take some extra time if needed. I mean, 10, 15 minutes is okay for sure. So if needed, of course, if you don't mind, of course.
I don't know. I see some raised hands, but I'm not sure whether these are old or new ones. So there's again.
Could I make a comment?
Yeah, please.
I just wanted to say, with reference to the discussion of a Lifshitz point, that if you look, again, it's basically, the point is that fluctuations are very important. And if you, there can't be a Lifshitz point in 4 or fewer spatial dimensions. Fluctuations will wipe that out, because the propagator will go like 1 over k squared squared. And I wanted also to mention, people asked what are possible physical signals. And with Valgushev and Renneke, we've been looking at this kind of pionic quantum spin liquid that we believe occurs, that it would contribute to quantities such as kurtosis and the like that have been measured by the Starr and Hades experiments in heavy ion collisions. And it will produce C3 over C2, C4 over C2 and the like. And we're doing an extended analysis using a blast wave. And lastly, I just wanted to say, I understand I'm touting my own horn, for which I apologize. If David Blaschke is still listening, that at 0 temperature, such fluctuations would also make the omega mu meson heavy. And some of you may know that one can get a stiff equation of state from a omega naught condensate. And then the question is, how do you get the equation of state to get softer again? And this is one way of doing that. If David's still there.
Yeah, I'm here, yes.
Okay. Because you've looked at these sort of models too.
Yeah,
right?
yeah. So, but can you repeat if there was a specific question? Of course, we have the omega 0.
No, it was a comment. So my question to you is, if the omega naught gets light, then you can get a stiff equation of state. How do you get the stiffness to go away? And one way of doing that is if the omega naught gets heavy, which could happen from strong fluctuations in pionic quantum spin liquid. I don't expect this to be comprehensible. It's just a comment.
Yeah.
I'm not really explaining things.
Would have been nice also to have a talk by you on this maybe, but okay.
The time difference gets a little difficult.
Yeah, that's tricky. I mean, the nice thing about these Zoom conferences is that we don't need to travel and you have all the experts together, but of course the time difference is the problem. Yeah, talking about time, maybe we should slowly conclude this session.